Hi everyone, are you able to hear me clearly and see my screen clearly? Hi Abhinav, hi Balaji, hi Bintao, hi Gopi, hi Kamal, Neerav, Noor, Pavan. Are you able to hear me and see my screen clearly? All right. So yesterday we talked about linear algebra and how to achieve the same thing using Python, specifically NumPy. So we are going to continue from where we have left off, which was the normal equation. All right. So this is basically the normal equation. Okay. SVD I'm skipping for now. We will talk about SVD in the linear algebra at a later point of time when we have when we need more details. All right. So don't worry. We're going to look at the linear algebra notebook after a while again when we need those concepts. All right. So yeah. Great. Great. So should we start? All right. So one more thing some of you have asked me about quick background on the differential. That will be really hard, but I can give you a quick background on the differential, but just very tiny bit. Okay, in case we have forgotten. All right. So what do we mean by differential? Again and again, we will be talking about d y by dt, dy by dx, error by d theta, and so on, right? So differential is nothing but computing the rate of change, okay? Computing the rate of change. So, so if let's say you have a curve like this, all right? If you have a curve like this, at any point, the slope of this curve is called the the is basically the slope of this line is equal to the derivative of the equation of the curve at that point. So what we do is, sorry, the screen was paused. Okay, so all right, can you see the curve now? All right. Okay, so if we are given a curve, at any point of time, the tangent can be quickly found, the slope of this tangent can be quickly found by computing the derivative or differential of this curve at that point. Okay, so in general, whenever we want to compute the rate of change, so we go at any point of the curve and we go a little ahead and then we compute the ratio between the two. Okay, let me show you in the Okay, so let's say this is the curve and we want to find out the the derivative at any point. So what we'll do is, you see this tiny square at that place, let's say here, what we do is we draw this, sorry, this looks like a curve. I'll just take a very small, so we'll draw this kind of a line. Okay, well, this is actually converting it into curve. So if we draw this at any point of time, what we do is, let's say this is the x. What we do is we go a little ahead in the curve, find out the value of y at this point, and then we basically, what we do is we basically compute how much y had changed, right? Y was this much, and as we went ahead, y went up, so y went became this, and at this, right? So the rate of change at any point is this is delta y, right? And this is delta x. So this is delta y and this is delta x. So if we have 2 points, this and this, okay, okay. If we have 2 points, right, one is this here, this is 1 point, and this is another point. Okay, if we have 2 points, here it was x and comma y, okay, and this was x plus delta y and here, and y plus delta y. So we were at this point, we wanted to compute the slope at this point, say. So what we do is we increase x by delta x and y by delta y, and then the slope of this line will be how much? Delta y divided by delta x. Okay, and as this delta x keeps on decreasing, both of these values keep on, we make it really tiny, we will be able to compute the differential. Okay, so generally at any point of time, this is how you compute the slope. Slope is dy by dx at any point of time. So this delta, when we put the constraints like delta x should be really tiny and so on. Okay, so at that point of time, what we do is, okay, at that point of time, so this basically this delta is written as dy by dx in very simple words. Okay, so slope at any point of time is the derivative, this is also called derivative or differential of the curve at that point of time. Okay, so generally the problem is finding this value at any point of time. So we have the differential calculus, the one that we studied, helps us finding this value at any point of x. Okay, at any point of x, this value can be computed. Okay, say for example, if y, this equation is, say, y equals x square, right? So dy by dx, or we simply write sometimes differential like y dash. So y dash is going to be 2x. Okay, this is the way we have figured out that after doing a bit of calculation, we figured out that differential of y at for any value of x is going to be 2x. Okay, so if we are given a curve like this, okay, if we are given a curve like this, it's going up. Let similar equation. So the derivative of this one is going to be twice of x at any value of x. Okay, is it clear to everyone? Neither? I see. I see. Okay. So which part is not clear? The how 2x squared became 2x? Okay. So let me explain again here. Let's say at any point, right? We are given a point like x and y, and we wanted to compute the slope at this point, right? So what we do is we move a tiny bit in x-axis, that's delta x. Delta x has to be very tiny so that whether you compute slope here or slope here, it should not make much of a difference. Okay, so we increase x by delta x, and then because of this change, how much y is changing? Okay, so if let's take a case of x square, what will happen is new y, let's say this was x1, this is y1. So the new y is going to be x plus delta x, right? And the square of it, correct? The new y is going to be x plus delta x and the square of it, which means it's going to be x square plus 2 delta x plus delta x square. Since delta x square is really huge, therefore we can ignore that part. Okay, so it's going to be x square plus delta x square plus 2x into delta x, correct? Let me just write it in a clear fashion. So it's going to be delta y, okay? Delta y is going to be x plus delta y. I'll just write d and dx, right? And the square of it, correct? Oh, what happened here? Why is not letting me write? Wow. Is there something wrong here? Wow. Okay, so let me see if I could just move it up. Right, never mind. So I'll just take another note. So what I'm saying is that if we know that y is equal to, say, okay, so let's say y is equal to x to the power 2, right? So it's going to be the next y2. If we increase x by delta, is going to be x plus delta x. Instead of writing delta, I'm going to write dx. Okay, then because it's big, so I'm just making it like this. All right, so it's going to be something like x square plus the delta x square, right, plus 2 into x into delta x. Okay, that's what was the differential that we have studied, correct? Now if we take a look at this equation, right? We can ignore this particular term because we are saying that delta x is really, really tiny. So delta x square is going to be further more tiny. Okay, so what we do is we convert this into we convert this into delta x. So, okay, x square plus 2 into x into x into delta x. All right. So this is the new y. This is the new y. And how much y had changed? How much y had changed? So delta y is equal to the new value of y minus old value of y, which was this. Okay. Minus what was the old value of y? X square, correct? So this is going to be 2 into x into dx, right? So dy by dx is equal to 2 into x. Is it clear now? So what we did was we took delta x plus delta x like this, okay? So what we did in this equation to calculate a newer value, which is a little higher for a little higher value of x. So we basically put, instead of x, we put x plus tiny bit of more value and then squared it. When we open it, we basically get this kind of equation. A plus b whole square is a square plus b square plus 2ab, right? And we are ignoring this part. We're ignoring this part. Why? Because this one we are ignoring because it's really tiny and hence we have this. All right. So this is a quick derivation or quick proof of why dy by dx is equal to x squared. Okay. In the same way, we have many formulas like the dy by dx of sine x is generally cos x and sine square x is uh, we apply chain rule there. In case of derivative, let's say had this been y equals sine of x whole square. Okay, so what we'll do is we will consider this as an expression and use the formula that we previously computed and say 2 of sine x, and then we say the derivative of sine x, which is cos x. Okay, so this way we can do the computation of derivatives without going through a lot of hassle. Okay, without going through a lot of hassle, what we have done is we have learned how to generally compute the value of the value of dy by dx. Yes. So whenever we say dy by dx, we are assuming the change in x is really tiny. Change in x is really tiny. All right. Is this clear to you? And when we say dy by dx, what it means generally is, okay, let me delete. Okay. Now question is how useful it is. Okay. How useful is the derivative? So you could do a lot of things with derivatives. So you could compute the rate of change of anything using this. Say, for example, given a tangent line or any slope, what we can do is we can always find out the slope of it. Now, you might ask that what is the use of a slope? Okay, let us say we are trying to find the maximum or minimum value. We are trying to find maximum or minimum value, right? So what we will do is, if we are trying to find maximum or minimum value, what we'll do is we'll find the place on this graph where the slope is 0. Okay, so that's one of the very big use cases of derivative. In many problem solving, in many hard problem solving, we could always use derivative to compute or find minimum or maximum. Okay, and that's the sole idea behind the normal equation that we talked in last time, that using derivative, what we will do is we will compute the derivative and we'll equate it to 0, and that way it's going to be, it's um, we'll find all uh, local minimum maximum. Let me just give you a quick demo. I think this will be better. Okay, so what you see is this slope that we are talking about, you can see how it's varying. So it's the value at the bottom is showing the derivative of, or slope of this line. If the slope is 0, that means the line is horizontal. If the slope is 1, that means the line is vertical. Okay, you can see that. A slope is big, that means the line is vertical. If slope is 0. Now you can see that at this point, approximately at this point, the slope is almost 0. Okay, when the curve is going downhill, the slope is negative. When the curve is going uphill, the slope is positive, and so on. So slope is equal to the derivative or differential dy by dx of at that point. Okay, so if we are given the equation of this curve, if we are given the equation of this curve, and we would like to find out the points at which the value is minimum or maximum, so what we'll do is we'll find the derivative of this one and equate it to 0, and then we will calculate all those values of x for which the derivative of this function is 0. All right, does it make sense to you? 0 means not, yeah, slope is, when slope is 0, it could be minimum or it could be maximum. Okay, the here you can see that at this point, these are various local minimas and maximas. Okay, yes, the slope is 0, but the value could be minimum or maximum. Okay, so it could be here, which is fx is really high. Here it's like highest, and it could be lowest at all these points, whether this as well as this. The slope of the line, the slope of the line is 0. Okay, also please note that the rate of change of slope, if we draw the rate of change of slope, we'll find that the rate of change of slope at this point is going up, is going from negative to positive. That means we are at minimum. If the slope goes from positive, being like this, to negative, that means we are at maxima. Okay, so if the uh, slope was 0, and before being 0, if we compare the value before and after being 0, we'll find out the whether a particular point was maxima or minima. All right. So given a big graph, like a complex graph, the way we have given in the diagram, if we compute the derivative of this expression and equate to 0, and then find out all those values of x for which the slope was 0, there will be many values of x for which the slope was 0, and all those values would represent these peaks, or the what do you call the lowest points, peaks and troughs. They will basically You will basically find these points where of points of local minima or maximum. Yeah. So peaks and valleys. Yeah. Okay. So I hope that gives you a quick refresher on the meaning of differential calculus. Okay. In the normal life, the differential rate of change of distance is velocity or speed. The rate of change of velocity is acceleration. Okay. So that's the physical significance. So wherever there is a change involved, wherever there is a change involved, either with respect to time or other feature, we generally think of derivatives. The other place where we think of derivatives is where we want to scan through a function and want to find out the point of minima or maxima. Okay. All right. So, I mean, there are many cases where we generally use derivatives. So let me take a case of a quick case of another case, because we will find out that the a lot of problem in data science is all about finding minima. Okay, let me take a non-approximation problem. Okay, so okay, so what we see is, imagine that you were here and there was a river. Okay, so and there is somebody drowning here. Okay, there is somebody drowning here, and this is where you are. Okay, now you can swim a little slower. You Okay, let me just move this point a bit up. All right, now let's say this is where you are. I hope everybody is okay with whatever we have studied today. We learned basics of differential. I'm hoping that most of you have studied differential calculus. This would generally serve as recall or refresher on what we have done earlier. Okay, so imagine that this side is the river. Okay, and this side is the ground. So your speed on the ground is generally faster than river, right? You can walk faster than you swim, right? Or you're a better swimmer. All right, so let's say somebody is drowning here and you want to basically rescue them. One way could have been that you start going from here till this point, and then start swimming to this side, right? That's what you'll do. You basically go in a straight line from here. Okay, all right. You basically start swimming straight. Okay, but you see that this line, if we could have, gone till here, right? Gone, say, till from here till here, and then just swam this much. So this swimming distance is smaller than this. Therefore, this could be a little bit faster than this, right? This could be a little faster than this. So, in these cases, what you do is you basically assume some point here, okay, x, and compute how much distance are you walking and how much distance are you swimming, okay, and find out the overall time and then minimize that, okay. So in many cases you will find in normal life that you can always you can always create an equation. Let's say a time equals or time taken is equals to a function of some t, okay, and okay, so function of x, sorry, not t, so it's a function of x. And then if you want to find out what is the optimum point to which you would like to walk and then swim, then what you'll do is you'll compute dt by dx and equal to 0. Okay, so here you'll find the x value. You will compute the x value, and this way you'll be able to basically save somebody quickly by knowing that. All right. So did this example confuse you or make your life easier? All right. All right. So the maximum value and minimum value can be found by some critical conditions such as endpoints. Yes. First derivative by equating first derivative to 0. So there are many applications. So this was one application of derivative. And the second example would be that we generally tend to say that things like rich gets richer, right? Rich gets richer. So what does it mean? If I ask you from the differential calculus perspective, what does it mean? Anyone? So how would you represent rich gets richer mathematically? Yes. Yes, it's a function of money versus time. Okay. Okay. So how would the equation look like? So if somebody says that um, rich gets richer, what does it mean? Or in the same way, the pages with more popularity will become more popular. Okay. Okay. Yes. Rate of change is greater than 0. But here, there's an important piece of information. Important piece of information is that rich is getting richer. Okay. So the rate of change is better for the people who are already rich. Correct? Yes, that's right, Gopi. That's right, Kamal and Gopi and Ross. So if we take a look at rate of change rate of money, let's say money I have d money by dt is a function of, let's say we put some constant, let's say some constant c into the money I already have. Okay. So, so the rate of change of money is directly proportional to the money I have. Okay, meaning if you think about interest, interest is rate of change of money is proportional to the money I have. Just that dt is not that small, like it's not increasing every second, it is increasing every year, right? So here, let's say somebody says in absolute term that rich gets richer every millisecond. Okay, so then we have the equation like this. All right, and when you different you basically compute the inverse of it, right? You'll be able to figure out that this is essentially this, okay, and some other constant. And then when you further go ahead and okay, so when you further go ahead, you'll find that it's something of this sort. Okay, so the money is all right. So the rate of change of money is proportional, is exponential. This is exponential. Here it's logarithmic on the left hand side. Okay, so rich gets richer is essentially meaning that the curve of money, the curve at which if we draw it, the money and the time, right, is going to be something really high. Okay, not like this. This became just too much. So something with this one. Yes. And the second derivative of the money, no matter in this equation, will always all the derivatives, no, nth derivatives is also going to be the exponential, because the if you differentiate the e as in the exponent, the exponential equation, you always get an exponent. So dy by dx of ex is always ex. Okay, so no matter how much time you differentiate, it's going to be ex. All right. Did this example make sense to you? So here at this point of time, I've tried to demonstrate the inverse of differential, which is logarithmic. So since we have already known this information that dm by when we differentiate something, if it is leading to 1 by m, it is log n. So if we differentiate log m by with respect to m, you're going to get 1 by m. Okay, so here m is money and t is time. Okay, so all right, I hope that doesn't sound very depressing to you. Okay, and yeah, all right, so these are the physical significance of the derivative. Derivative is a very, very important thing. It's valid for things which are continuous. So we will require and assume that you know bit of derivative, a bit of differential. We call differential derivative and dy by dx same thing. Okay, or rate of change or slope. It's the same thing. All right. Yes. Should we move on? All right. So we learned some things just now. Okay. So we did a quick refresher of what is differential calculus and how it helps in many ways. So you'll find that a lot of problems could be solved this way. Okay. So this equation, the normal equation, is exactly this. So what we do is we let's say we want to fit the data in the curve. Okay, this example would help you really much. I'm also giving you this copy. This is something I've not planned, but yeah. So let me just walk you through this example. That'll be easier. Imagine that you had some data points. Okay, you had some data points, and what you do is you want to draw a line that is the best. Okay, so what we do in these cases is we assume a line with beta 1 and beta 2. Beta 1 is the we assume the line with beta 1 and beta 2. This is the line that we are assuming. Okay, all right, now we have to find exactly the value of beta 1 and beta 2 so that we know the so that we know which line is perfectly fitting this. Okay, so one of the approaches that I just discussed was, as in case of saving somebody from drowning. Similar to that one, what we do is we are going to form a equation, and then we are going to differentiate and equate it to zero. Okay, so here we put, these are the data points we are given, which are given to us. These are the data points. These are the data points given, we have plotted here. So for first one, we are going to say beta 1, because y, this is the equation that we are assuming, y equals beta 1 plus beta 2 x. Okay, in our case is theta 1 and theta 2, theta 0 and theta 1, and so on. So what you see here is the when we put these data points in this equation, what we get is b1 plus 1 into beta 1. Okay, x is 1, right, and y is 6. Similarly, when we put all the four points here, we get this. Now let's compute how far are we from the actual value. So what we do is we subtract the actual value. Okay, so this is supposed to be equal to 6, this is supposed to be equal to 5, and so on. But since the line is not really going through, this line is not going through all of the points, therefore there is an error in each of them. Okay, so we need to subtract this predicted value from the actual value, and that's the error. So what we do is we square the error everywhere, and this is the final value that we found. Okay, so this is the predicted value as per our hypothesis. This is our hypothesis in this case, and this is the actual value. Okay, 6 is the actual value, beta 1 plus beta 2 is the hypothesis. So the delta of the two is the error. So that's the error we compute in all four cases, and we get this formula. Now, if we if we differentiate if we differentiate this equation with respect to beta 1 and equate it to 0, we will find the value of beta 1, that is that will lead a minimum value for this one, as well as we will, if we differentiate this overall error with respect to beta 2, we are going to get the value of b, as in we are going to get, okay, let me put it again. So what we did was we created a hypothesis, that is our linear equation. Okay, this is our linear equation, that's our hypothesis, and we are fitting these data points into this linear equation. Okay, and whatever value are we getting, we are subtracting from actual, that's our error, and we want to minimize this error, right? And how do we minimize things? By computing the points where the slope is 0. So we first differentiated it with beta 1 and equated it to 0, then we differentiated it to beta 2, and equated to 0. So we got two equations to solve. And when we solve these two linear equations, we can solve these two linear equations easily, right? And if we had n number of assumptions, right? If we had n more, let's say we had beta 3, then we will differentiate this overall error with respect to beta 3 and equate it to 0. Okay, then we'll get three linear equations to solve. And when to solve these three linear equations, we can apply whatever we have learned in past. Okay, and there we can compute our beta 1 and beta 2. Okay, all right, let me just give you the, all right, so does it make sense to you, the beta 1 and beta 2? So this way we computed the value of beta 1 and beta 2, and the we can find out the various values of y for each x now. Okay, that means we'll be able to do the predictions now. Does it make sense to you? Mm. All right. So this is basically, this method of doing the computation is what we call the normal equation. Okay. This method of computation is what we call normal equation. And this normal equation is true in the case of linear equations. All right. Abhinav, Balaji, Bintao, Gigi, Gopi, Kamal, Neerav, Noor, Pavan, Pratik, Ross, and so Shahrukh. Okay. A question from Kamal is, in this example, can you define matrices like capital X? Good question. So, all right. So, what is our capital X in this case? Okay. So these are the data points. So for X is the input variable, Y is the output variable. So here, right? Anybody? So capital X is, okay, capital X is, including the X naught, I'm just putting the X naught with it. Okay. Sorry. 1, 2, oh, this is pretty simple. And 4, correct? All right. So, okay. So the truth is that the maths is actually required uh, in many disciplines. It's just that we fail to overlook that part. And this is a question that a lot of people actually ask me, that in software engineering we hardly ever needed maths and we hardly needed differential calculus. So I have countless examples of math being applied in the computing. The product which I built for Amazon, when I had to prove that this is the best approach, this is the most fastest way, I had to put down the numbers. I had to show them the rate at which the progress will happen. There, I needed fair amount of maths. Similarly, at in Mobi, in one of the monetization models, we figured out that if we are displaying search result in particular way, we are going to get a lot of hits. And there we needed to compute what is the amount of feedback we will get. So even though at first it looked like that the maths is not required for this kind of calculation. This is hunch, but it was a mathematical problem. And that is something very important that we learn as part of machine learning discipline, that that a lot of problems can be solved very well using maths. Okay, so keep the math hat on when we are trying to solve a problem. And for that matter, a lot of engineering students ask me, or a lot of senior engineers ask me that, do we need so much of, say, data structures or things like that for the computation in for solving large scale problem in organizations? My answer is yes, we do. Whenever we want to optimize things, whenever we want to make things happen which have not happened before, then we would require maths and all the science that we have studied. Okay, and it would come in the package that you won't recognize. Okay, the problem would come in a package that you won't recognize that it is the math. All right. All right. So yes, you are right. So math is applied. It's just that we kind of oversee it. And I'm talking about all the candidates I've worked with in my past 15 years of experience. People who have really good experience in, they have been maths Olympiad champions in past, and still they fail to see the application in the normal work. Okay. So the only reason is that we don't look at the work in the way we should be looking at. Now, mm, I mean, I have a lot of war stories I can go on, but yeah, the summary is that whenever we are solving a problem, we should solve it with all possible things, whether it's differential calculus or whether it's an iterative approach, whether we want to apply a predictive formula and so on. And it is doubly true when we are solving a machine learning problem, that one is just use the iterative approaches, that the usual iterative approaches. The other is use a little bit of mathematical entities, or the most important part is the objective function that we define in our problems. It generally requires maths. Okay, like for example, rich gets richer was one such case that people seem to overlook the statement and not figure out that this is basically a differential equation. Okay, and the same case is with many more examples that you will encounter in future, that we could generally express a lot of entities with maths. Okay, now coming back to the problem, so this is how the matrix looks like. Okay, so and the small y is 6, 5, 7, and 10. Okay, good, wonderful. So this is am I making a mistake somewhere? Yeah, it's going to be a column matrix, but we can always put it that way. We could always do a transpose, right? All right. So then basically this is what we are going to do in this case. And these are thetas instead of betas. Okay. I'll just go back to, so y hat is the optimum solution, right? No, this is, you're right. So what is y hat? Y hat is going to be, y hat is going to be, all right. Let me just tell you. Y hat is predicted value, okay? All right. So let's go back to the equation. All right, let me open my notebook. Where is my notebook? Let me just open it and then we can discuss. All right, so I hope this is what we're doing here. That's right. Let's just see. All right, so it is coming out to be, for me, it's coming out to be 3.5 and 1.4. Where is that? 3.5 and 1.4. All right, so does it make sense to you, Kamal? Uh, Question from Kamal, can you show the equation y hat equals theta transpose x? Okay, the y hat equals theta transpose x. Okay, is that one? So here we are assuming that our y hat is basically a function of axis. Okay, and what you see here is basically this is the equation that we're talking about, the assumption that we have made. So y hat is the predicted value. Okay, so y hat in my case, we don't have to, uh, that's something that is going to be computed every time. So y hat is going to be whatever betas we are assuming. Theta is our assumption, by the way. Thetas are our assumption. Thetas are the variables that we are going to solve it for. Okay, so thetas are our assumption. X is given, and what we are going to do is we are going to um, subtract it and then do that. Okay, so y hat in this equation is this. Y hat is, this is y hat. Okay, this is y hat, this is y hat, this is y hat, this is y hat. All right, so theta is basically an array of beta 1, beta 2, and so on. Okay, in our case, the thetas are those values. Instead of this here, betas, we have thetas. That's all. All right. So we're going to, again, instead of thetas, we have betas, and this is basically, it's this is what we want to do actually, but it is not really true since there is always an error here. There cannot be a line that fits through all. So this is not really right way to write it. Okay. So what we're going to do is whatever betas we have, we first find out the overall error. We got this error. We differentiate this error with respect to all of the thetas. And then that's right, Noor. Okay. All right. Is it clear to everyone? So this was our, so what we did was the same thing that we have on the Wikipedia link, the same thing we have solved using our formula here, using normal equation. Okay, and this is essentially, this is what the normal equation does. Here, when we see the inverse and everything, they are basically solving these linear equations. They're basically solving these linear equations. Okay. All right. So normal equation, that the one that we have been talking about, this normal equation is valid only for linear equations. Okay, it's not really valid for the nonlinear ones. So here our assumption is that our data is fitting in a straight line, and we are trying to figure out that straight line. Also, in this case, we had only one independent variable called x. There could have been more such variables or features. Okay, good. So normal equation is okay. Let me push the Git this one to the Git repo. Should I copy paste this code? Let me just push. Okay. Also, let me just open one terminal. Wonderful, wonderful. So we really learned something today. We basically understood the underneath of the differential calculus. We also learned the significance of dy by dx. Also, we learned about solving the solving the linear regression problem by hand, as well as using the normal equation. All right. Okay. So the this is the first machine learning model that we used to do in most of the cases, that we'll basically plot things on a whiteboard, draw a straight line through it, find out which straight line fits the data, and then start predicting using that straight line. Okay, that's the easiest thing, and that's probably the oldest technique to solve such to do the prediction. Okay, so this one is not iterative. This is non-iterative approach. Normal equation is not non-iterative. Why? Because here what we are doing is we are solving these equations. Basically, we are solving these linear equations parallelly and finding the value. Okay, here we are not iterating. So we found that formula in terms of all the thetas, and then we differentiated with respect to each theta, equated to 0, and then using those equations, we solve these equations, and using these equations, the solution of these equations, we found the value of thetas. Okay, so it's non-iterative approach, and it's a good non-iterative approach. And the only problem is that while we solve these equations, right, linear equations that we saw here, so here you see these are the two equations that we get. Okay, this is the overall error, and when we differentiate the error with respect to each of the thetas or betas, we get these n number of equations. Solving these n number of equations is really heavy. Solving these n number of equations really heavy because it involves O n cube, as in if there are n number of features, the total number of equations that are going to be, they are going to be n square. Okay, and therefore the overall complexity is going to be n cube. Right? How do we solve the equations? We take two equations, eliminate one of the variables and so on. So the variable elimination things that we studied in algebra, it's actually a complex process. It takes it's a time consuming process for the computers. Therefore we rarely use, or we never use, the normal equation. We generally use iterative approaches. Iterative approaches are better than these. And also the normal equation is great only if the data that you're trying to fit is having a linear relationship. Had it been some other curve, we won't be able to solve these equations so easily, right? Because they won't be linear. All right, a question from Noor, but then we have to get this for all features. So then we have to find a common point of all features. Correct, correct. So, right, right. Great. So this is what we studied last time. So it is a good recap of the entire thing. All right. So the normal equation is linear with regards to the number of instances in the training set. So it handles large training set efficiently, provided they can fit in the memory. Okay. So you can see that if you double the number of features, what will happen is the time complexity basically it'll take 8 times. Okay, if the features are 10, from one feature the total number of variables or total number of input variables became 10, the time taken will become 1,000 times. That's why normal equation gets really slow when the number of features grow larger. Okay, so all right, so total number of instances, it doesn't so for normal equation, the number of instances, it doesn't it is not dependent on, it is not dependent on number of input data instances. So it's linear with respect to the training set. So no matter what is m, m is total number of rows in capital X. No matter what is m, it'll be able to handle that. Okay, provided they can fit in the memory and it's a linear equation. So let's explore different ways to train a linear regression model, which are best suited for the cases where there are a large number of features or too many training instances to fit in the memory. So the normal equation where we computed the differential of error and equated it 0 and computed those beta 1 and beta 2 or theta 1 and theta 2. So in that case, if the features are small, as in there are a small number of features, and okay, let me repeat what I'm saying. So if there are less number of features and the equation is linear, normal equation is the best. Okay, but if features are hundreds, and if features are 100 and we won't be able to use the normal equation because it would take a lot of time. Now That's where the iterative approaches come into play. Iterative approach, the first iterative approach that we're mostly going to talk about in linear regression. Let's understand the gradient descent. Okay, so this is something which we have talked again and again. If you are lost in the mountains in a dense fog and you can only feel the slope of the ground below your feet, which strategy will you take to reach the bottom of the valley quickly? Okay, so what you're going to do is you're going to take a step. If the step is downhill, keep walking faster in the same direction. If if it is if it is not, if it is uphill, take the reverse direction and repeat the step until you reach the bottom. Okay, until you reach the bottom. So in any curve, wherever we are trying to optimize, this could be the approach. Okay, in the normal equation, what we did was given a curve like this, when we wanted to find minima or maxima, what we did was we did dy by dx, as in we computed the slope. Okay, we computed the slope in terms of x, and then we equated that to 0 and found that value of x at which the slope was 0. Okay, in this approach, in the gradient descent approach, what we do is instead of that way, what we do is we basically compute the slope at every point. If the slope is up or down, based on the slope at every point, we we go to another point. So if the slope is down the hill, we move ahead and go to next point and again compute the slope and then do the thing again and again. All right, that's what is the approach called gradient descent. Okay, because the approach where we compute the slope and equate it to 0 may not lead to solutions all the time. Okay, because if the equation is complex, we can't really rely on solving an equation. Okay, all right, using say dy by dx equal to 0 and then trying to find out what is the value of x on which it will go 0, that is not really solvable at many points. Okay, so instead we use the iterative approach. Iterative approach is gradient descent, whereby at every point what we do is we compute the slope. In case slope is steep, we just go faster towards the downside. If the slope is shallow, we go slower, and so on. Okay, and when the slope is really shallow, as in the slope becomes horizontal, it will stop. Okay, so this is the gradient descent way of getting getting to the minimum. While in the normal equation, we differentiated the graph that was we differentiated the error and found the minimum here by equating it to 0 and solving for x and y, theta, solving for theta 1, theta 2, theta 3, and so on. Okay, here what we're doing is we are going iterative. All right, so gradient descent measures the, so you don't have to remember any of these formulas, by the way. Okay, and yeah, you can always use the standard libraries, or you can just search on Google and you can always find these formulas. Okay, so gradient descent is basically an iterative approach. All right. So gradient descent measures the local gradient of the cost function. Okay. So again, gradient is also same as differential. Okay. Gradient is same as the slope. Okay. And so gradient descent measures the gradient of the local cost function with regards to the parameter vector theta, and it goes in the direction of descending gradient. Okay, and until the gradient becomes zero. Okay, so gradient is let me further go ahead. So okay, question from Bintao. The second derivative is more negative once it becomes to positive. That means you have come to the bottom. That's right. The second derivative will start to become positive after this. So basically the rate of change of as you increase x, if the rate of second derivative is positive, that means you are on minima. If second derivative is negative, then you are at maximum. Okay. Okay. So here, what we are trying to do is we are trying to find out at every point, how is our error. So here, the thing that we are trying to minimize is our error. Okay. That's the thing that we are trying to minimize, the MSE. So the at at every point, what we do is we compute the rate of change of error, and in case the rate of change of error is negative, we start keep on going. If the rate of change is positive, which means the error is increasing, then we go in the opposite direction and keep moving. Okay, this is what we do. All right, so we at every point we compute the slope, and if that slope is up or down, based on that we take a call whether to go down or whether to go up. All right, so we start with filling theta with random values. Okay, so let me go up, and I think we'll come back to that same equation. So theta is what? Theta is the coefficient that we are trying to figure out, and we start with random thetas. We start with random initial values. Okay, and then we improve gradually, taking one step at a time. Each step attempts to decrease the cost function, the overall mean square error. Okay, and until the algorithm converges to a minimum. Okay, so gradient descent can solve every kind of equations, whether linear, nonlinear, every kind of equations, while the normal equation can only solve the linear ones. Okay, so coming back to it, so I hope this is very clear to all of you. So we start with initial values of theta. So what we are trying to do is we are trying to find out all the thetas, all the coefficients. Again, let me go back to the, okay, let me go back to the equation. So yeah, so this is our mean square error. This is our mean square error. And here thetas are, it's a linear equation. So in the linear equation, we have if the so y hat is equal to some kind of a hypothetical function of x. the thing that we are trying to figure out. That's the meaning of life and everything. So for given set of x's and set of y's, what we want to do is we want to figure out this h naught. For now, let's assume that h naught is linear. That means we can express it like a set of linear equations saying uh, b1 saying x1 plus x1 into slope plus y-intercept and so on, right? So thetas are those coefficients. Thetas are those coefficients. So if this is how the y hat looks like. So y hat is equal to theta naught plus theta 1 plus theta 2 and theta n, and the same thing could be expressed in the linear algebra by multiplying theta t with theta t with theta with x. Okay, all right. So either we multiply with we here theta also has n number of elements and x also has n number of elements because we're going to put one here, and theta dot t theta dot x is something that we need. All right, theta t means all the thetas, instead of being horizontal, they become vertical, and when we multiply with x, which is horizontal, all the values will become vertical. Okay, so this is what it is, and this is what we are trying to predict. So thetas are nothing but the coefficients of our equation. Okay, now moving back to gradient descent. All right, so all right, now here there are few things that we should talk about. One is from where the point we start at any point. So do we start with, what we do is we start with any random points. Okay, all values of theta. So on y-axis we have the overall cost, and on x-axis we have the thetas. Okay, there would be many such axes, theta 1, theta 2, theta 3, theta 4, and so on in n dimensions. Okay, right now we are plotting it against one of the theta. Okay, against one of the theta. So here we are just showing that we are moving only in one direction. We are only first assuming some value of theta, some value of initial coefficient, and then measuring whether the slope is up or down. If slope is down, let's keep on going, increase theta further, and then check if the slope is still down. If it is still down, keep on going faster and faster. Keep on going in that direction. If the slope is steep, we go faster. If the slope is not steep, we go slower. Okay, this is called the learning rate. Okay, so the size of steps, also called as learning rate, plays an important role. Okay, so learning rate is in what proportion of the slope we would move fast. Okay, just like if something is really steep, we move faster. In the same way, learning rate is a number. Learning rate is a coefficient, or you can say hyperparameter, that we would have to feed for our algorithm. So we need to decide whether to keep learning rate high, in what proportion of the slope we should move. Okay, so the algorithm will have to go through many iterations if the learning rate is really small, which will take a long time. Okay, so learning rate is kind of a parameter that we might have to specify. If we specify learning rate to be high, okay, so let me go here. So how big a step should we take? So the step has to be in the proportion of the slope that we all agree. If the slope is steeper, we go faster, but how much? Should we say 2x of the slope? Should we say 3x? Should we say 5x? Right? That is the learning rate. Okay. if the learning rate is too low, what will happen is it'll take forever to reach to the bottom. Okay. If the learning rate is too high, what could happen is let's say we were here, okay, and learning rate is high. So instead of going here, we might go here. That if learning rate is, let's say the next value of x that we're going to, next value of theta that we're going to try is this much. If our learning rate is this, so we might go up. Okay, so we could actually keep going up. So let's say we are starting here and our learning rate is this much. Okay, since the slope is down, so the learning rate would take us here, and then further the slope is gone up, so we could come back here and go back. So instead of going down, we are going up, just because learning rate is too high. All right. Now, the other problem that gradient descent suffers from is the global and local minima problem. Okay, so yeah, question from Noor is, so learning rate is a constant or function of something. So should we do iteration of multiple learning rate just to avoid jumping over the minimum point? Yes, we'll come back to that. So learning rate, we have to keep, we have to try with different learning rate and figure out which one is the best for us. Okay, there are few more techniques that we could use to decide the learning rate. Okay, and remember our hyperparameter optimization. So these are going to be the hyperparameter optimizations in future, right? You remember grid CV there. Okay, we will also cover how to decide the learning rate a little bit more. Okay, so we have to be aware that even though the algorithm is correct and everything, if the learning rate is wrong, we would never converge. Okay, now not all cost functions have a single convex point. There could be the functions which have multiple lower points, right? So there could be holes, ridges, plateaus, and all sorts of irregular terrains, making convergence really difficult. So sometimes when you have this kind of situation, the initial point where you are starting from matters a lot, right? So let's say we are starting here. So we end up here as per the gradient descent algorithm, and we would not go up any further. Okay. While our global minima is here, we would basically be satisfied here. Okay, so the initial point where we are starting from plays a big role. Okay, in the gradient descent, the standard gradient descent. Therefore, we have to come up with something so that we can reach to the global minima instead of local minima. If we start from the left, then gradient descent converges to local minima, which is not not as good as the global minimum. Okay, but if we are starting, our starting point is towards the right. Okay, towards the right, it'll take a very long time to cross the plateau, and if we stop too early, then we will never reach the global minima. Okay, if we started here or here, we will quickly reach global minima, but we started here, it will start thinking at this point that we have kind of reached the local minima. Okay, and therefore for the non-bowl kind of curves, the gradient descent may not perform really great. Okay, the MSE cost function is a convex function. When we draw something like the MSE equals y square, right? That is convex because it has a square term in it. And since the if you draw y square, you will see that there is a a it looks like a parabola, and it is on the it's like a bowl. Okay, so so MSE, the mean square error, is a convex function. Why? Because it has a single minimum point. Okay, now how do we find out which functions, and how do we define what's a convex function? If we pick any two random points on the curve, if the line joining them never intercepts with the curve, then we call that as the convex function. Okay, it has no local minima, it has only one global minimum. Okay, so that's the definition of convex function. So whenever we are using gradient descent, we must make sure that we do the feature scaling. We should use the standard scalar class from scikit-learn. Otherwise, the converging might take a long time, because for some of the parameters it would look like a plateau. For some it would look like steep, right? And therefore, when you do the standard scaling, just like we did in case of when we were displaying the errors, remember when we were displaying the errors in classification, when we were showing the images in the last, when we were doing the analysis of the images, uh, analysis of the digits, right? That's what we are doing. At that point of time, we realized that the error that we have there. Okay, let me go back what I'm trying to say. So standardization generally makes the things easier, right? Visually, in the classification case, when we were representing our results, until we standardized the results, we could not differentiate between one lighter than others. Everything looked dark, right? Therefore, standard scaling, in the similar way, standard scalar or standardization, or if the or making all the features on the similar scale will make gradient descent also work better. It'll be able to differentiate between one feature and another. It will be able to compute the rate of change of the feature easily, and would be able to go down the slope easily if there is slope. Had it been a flat terrain, it'll be really difficult. Okay. Yes, we are talking about the feature scaling. All right. Would standardization reduce noise in images for MNIST? It won't reduce noise, but it will make the the noise stand out clear. Okay, and the images would look less noisy. Now, going ahead, so all right, so let's take a very good question from Kamal, that if we have the cost function is a convex function. So if you draw any curve, okay, let's just draw some curve. Okay, so let's say this is our, okay, so let's say instead of this we are drawing it like this. Okay, Here also, if we take any 2 points, whether this or this or this, if we draw a line through this, it'll never cross the, none of these lines is intercepting the curve more than twice. Okay, it's not intercepting the curve more than twice. Okay, so that's how you can generally visualize this. Okay, so these lines are intercepting the curve only once. Okay, good question, Kamal. Is there a they yeah, is there a scikit-learn function? Let me just note it down if we could figure this out. Okay. All right. I mean, the correct way to do it would be you just go over the points on the line and see where it intercept. Is it intercepting with the curve or not? Okay. The other way would be to put the formula y equals to mx plus c in the curve and then solve it for x. If there are multiple values of x, that means there are multiple points and so on. Okay. Also, there is another, actually, there is another way of doing it. If we differentiate a function, and equate it to 0, if there are multiple values that are coming out of it, that means it has multiple minimas and multiple maximas. Okay, so that's another way of putting it. Say, for example, okay, so here we have y equals mx plus c, and here let's say we have y squared plus equals 4x. And so we could say mx plus c equals 4x and then solve it for x. Okay, that way. All right, let me share the, I think I've already shared this. Okay. All right, let's move ahead. The other way I was talking about is that you just differentiate the function, equate it to 0. If there are multiple values of x instead of 1, then it's a non-convex function. Okay, now the other problem that occurs with gradient descent is if you do not do feature scaling, what will happen is the curve will look like this. Okay, if you are, let's say there are, now let here we were representing our cost on y-axis, right? And we were only representing it as theta. Okay, so this same curve, if we plot it on with two thetas, as in two thetas, theta 1 on x-axis, theta 2 on y-axis, this and z-axis is the cost. Okay, z-axis is the cost, and the color in this the color in this shows that this is the, on z-axis this is the higher value, and the white one means lower value. So you can see the color gradient. So this is the highest value, this is the lower value, and this is, so it's a big bowl in which if you drop something here, it's going to go down till here. Okay, so if we have two features, theta 1 and theta 2, okay, and theta 1 and theta 2. So in that case, if we okay, if we have two features, theta 1 and theta 2, and we plot the graph like this with the cost function, in case the features are scaled, okay, if the features are scaled, what will happen is that it will go uniformly, because both increasing theta 1 and theta 2 both will happen by equal amount, so the line will look like linear, right? Because both theta 1 and theta 2 has the same scale. And what is feature scaling? We convert them from 0 to 1, right? So theta 1 will vary from 0 to 1. Similarly, theta 2 will vary from 0 to 1. And that way, and please note that we are talking about thetas, and why feature scaling has impact on thetas, because if we scale all the features in a linear equation, we are basically making all axes on a similar lines. Therefore, the role that will be played by each theta will be proportional to will be very much in the lines with the features. Okay, in the lines with the features. So, all right. So let's take a break at this point, and we'll be back soon. All right. So I'm back. Should we start now? All right. All right. All right. A question from Kamal. MSE cost function is a convex function. Is this a stated as fact, or do we need to verify it? So MSE in case of linear regression definitely is convex function. Okay. And it's kind of a if you try to draw the graph of MSE, you'll find that since it's a square and there are uh, values of feature y with respect to x, you'll find that it's actually a convex function. Okay. So as per my understanding, for linear regression, it is definitely the convex function. I'm not sure about the other regression because it could have multiple hills. Because if there is the underlying equation is nonlinear. Okay. So as per my understanding, for linear is definitely convex, but for the nonlinear, I'm not sure. I'll have to check. Great. So let's start. We were talking about feature scaling. Let's try to understand the graph first. Imagine that we had, instead of plotting one feature against against the cost, we have two features, theta 1 and theta 2, and the cost. Not two features, as in these are, instead of having only one coefficient, or let's just call them thetas, and these are the those coefficient of x that we are trying to figure out, these are the model parameters, or these are the end result of machine learning or the whole computation. Okay, so as one theta grows, the cost may go down, may go up, right? So we have to find that value of theta for which the overall cost is minimum. Cost is the deviation from the actual, that is the cost, overall deviation from actual. Here it's mean square error. Okay, so we have to minimize the error or the cost. Okay, it's the same thing. So here in this diagram, we have two thetas, theta 1 and theta 2. And when we are when we plot it with the cost, there are going to be three variables. Cost is on the z-axis, okay? And instead of showing z-axis in the diagram, we are showing z-axis in terms of color, okay? So the outer ring, the dark one, shows the high cost, while the inner ring, the white, this is showing the very small cost, okay? So if you think about it, it's like this one, adding one more axis, this becomes z-axis, this is x-axis, and on one more y-axis. So this is the way it comes out to be. Now, if the features are scaled, what would happen is both features, the thetas are also going to be very much similar to features. Feature scaling as in we bring down the features to between certain values like 0 and 1 and everything in between. So if we do that, the chances of thetas being in the same proportion or in the same scale is very high. And when theta 1 and theta 2 are on the same scale, the this chart will look like this. Why? Because at every step, we are going to decrease theta 1 as well as we are going to decrease theta 2. Okay. So at every step, we are going to decrease theta 1 and theta 2. Theta 1 and theta 2. So both of them, we are going to decrease in a single step, right? Therefore, if both the steps are of the similar size, this line is going to be very much pointing to the lowest cost point. Okay, therefore it will be quite linear as opposed to this one. Here, theta 1 and theta 2 are on different scales. Therefore, the change in theta 2 is going to be tiny, while change in theta 1 going to be bigger, and therefore instead of going straight, it's going to take a while to go there. Okay. All right. A question from Pawan. Non-linear can be converted to linear function. Sometimes we can, sometimes we can't. We can, yes, we can approximate non-linear functions with linear ones, but sometimes the error becomes too high. Is that what you meant? Okay. So basically the feature scaling is important aspect of gradient descent. Now, so gradient descent algorithm almost goes orthogonal to the direction of global minimum, okay? And it ends with a long march down a flat valley. When the slope is lower, the overall rate at which it will move will be really slow, and it will eventually reach minimum, but it will take a long time. All right. Now, the same diagram, what we drew earlier, could be drawn in this three-dimensional space. Okay, we have feature 1 here, x, feature 2 here, and this is the cost. Okay, at some value of x and y, this cost is going to be lower. Okay, is this diagram clear to all? So if y and x are the y and x are on similar scales. If okay, let me go back here. So here we have the only difference between the other graph and this one is here we have plotted the cost function with respect to thetas, and here we have uh, drawn the cost function with respect to the actual feature values. Okay, yes, go ahead, Noor. Yes, cost function, basically gradient descent will only find local minima. Cost function will depend, will be, cost function basically represent the overall cost at any point. Okay, gradient descent's role is to find that cost, minimum cost of that cost function. It will try its best to, our objective is to find the global minima, but the usual gradient descent would always end up with the local minima. Okay, so it's a function of where are we starting from. Good question. So that's what we are coming to next, that how do we avoid the local minimas. Okay, a question from Gopi. In this case, it is convex shape. Gradient descent can still handle inverse x squared. Inverse x squared. Okay, okay. So the gradient descent is going to be generally this kind of a shape because it's going to be the MSE. But whatever kind of shape it is, this shape looks really perfect. But in the cases if it is the other kind of shape, let's say we have a different shape here. Let's say we have a shape like this. So there also let's say this, right? That's the example we took. So here we are here. So we might go this side instead of going this side. So those kind of scenarios, gradient descent doesn't work well, and therefore we need to figure out alternatives there. So those are the alternatives that we're going to go ahead and we'll discuss those alternatives. Okay, there are minor corrections to the standard gradient algorithms, which will help us solve those kind of situations. All right. In the ideal case, this is how it's going to look like. Again, remember that training a model means searching for best model parameters, or we call them theta 0, theta 1, and so on. Okay. And the search is for these model parameters so that we can find the minimum cost. Okay, so we have to find all thetas that minimize the cost functions like MSE. Algorithms will have to search in more dimensions if model has more features and search becomes complex. Okay, so if there are more features, there'll be more number of if there are more number of features, there will be more number of thetas or more number of model parameters, and hence the search becomes more complex. Now, there are slight variants of gradient descents. There are basically three kind of variants. One is the standard batch gradient descent. That's the one which we have talked about. The second is stochastic. Third is mini batch. So we're going to implement one at a time and take a look at it. All right. So batch gradient descent is basically uses partial derivatives. We are going to implement gradient descent, first initialize all of the model parameters with random values, and then for each of the weights, we change only one weight, keeping the others fixed. Okay, let me put it this way. So we expressed our we express that our data has n number of features. Okay, we express that our data has n number of features, meaning our output depends on those n number of features. Okay, and for training data set, we have say m number of such data we are given that, and based on that, we need to learn and figure out the relationship between various features and the output. Correct? Now, the initially we will initially we are assuming that it's a linear regression. Okay, we are assuming that the output is a linear function of all our input variables. Okay, and instead of simply summing them up, what we are doing is we are multiplying each of the features with as model parameters. Okay, and those model parameters would decide the kind of relationship our output has with the input data. All the input x variables will be how they are correlated with the y. That's what we need to figure out. And for that, we need to find out all thetas or model parameters. Okay, so for each of the weights, what we do is for each of the theta, we we change one of the theta and see how is the output changing. Okay, what is the rate of change for each of the theta value? And then we do that for each of the theta separately. So we do the partial derivative. We do the way we did where did the yeah, the way we did partial derivative here. So we had this equation here. Okay, so here this is an example of a partial derivative. Okay, so when we are differentiating this equation with respect to beta, beta 2 is considered constant. Therefore, it becomes 8 beta 1, this becomes 0, and this becomes 20 beta 1, 20 beta 2, because when we differentiate something with this, it becomes singular value. And then when this becomes 56, and all of these becomes 0, because when we are differentiating something with beta 1, other things are considered as constant, right? Similarly, okay, so let me just take out this. Okay, so what we are going to do is we are going to differentiate, we are going to compute the differentiation of the cost function with respect to each of the thetas, each of the model parameters, and then we will compute the actual value of that partial derivative by putting our assumed value of thetas. Okay, and then we'll basically calculate the rate of change of the cost. This is called partial derivative. So it is like when we were at the mountain, right? With our we on a dense fog or blindfolded. So what we do is instead of computing the how should I say, computing the slope in any direction, what we do is we finalize two directions. Okay, one is east and other is north. So one is east, other is north. So we take a step keeping our we take a step straight in the east, straight to the east, facing east, and compute the slope. Then before moving further, we compute the slope to the north. Okay, so on both the directions we compute the slope, and then based on whether the slope is going uh, down or up, we compute the next point by combining both of the values. Okay, so we fall down, we either, if let's say in towards east as well as towards east as well as towards north, both sides we are going down, as in the slope is down. Therefore, what we'll do is we will basically choose a coordinate which is a combination of both. Okay, this will become more clear when we talk about this. So in general, we compute the gradient of the cost function with regards to each model parameters. Below is the equation for finding partial derivative of the cost function with respect to the model parameter theta, right? So this was our y hat. Y hat is here linear equation. So it's theta t and xi, and we are subtracting yi from it. And then when we differentiate this with respect to any of the theta, this is what we get. This is what we get. Okay. All right. So if we just say theta 1, right? So, and here there is a, it's a list of theta. So this is what we will get for with respect to each of thetas. Okay. In this equation, we calculate the partial derivative of each parameter theta j individually, and instead we compute them. Okay. Yeah. So basically the idea is to calculate the partial derivative of each parameter theta j, or we can also compute all of them in a single go, okay, using this kind of a formula. All right. So this is how the MSE, the rate of change of MSE with respect to theta looks like. And here with in every dimension, in every first we compute the rate of change of MSE, rate of change of cost with respect to theta 0, rate of change of uh, MSE with respect to theta 1, and so on. So basically we are differentiating the error function. We are differentiating the error function with respect to the model parameters, okay, in order to find those theta values, those model parameters, which basically are giving us the best smallest cost. Okay, so right now we just trying to find out the rate of change of MSE with respect to all thetas, and that can be calculated quickly using this kind of formula. Okay, this kind of formula. Now, so this formula involves calculation over the full range of x at every step. So theta j is not features. Theta j is basically the model parameters that we are trying to compute. We start with the initial value, and every step we are computing the rate of change of cost with respect to each of the thetas. And then once we compute it, we basically would decrease thetas with some amount of values. Okay. Okay. A question from Gopi is, what is 2 by m, right? 2 by m is what? We are basically, let me just go back here. Here, this was the mean square error, mean, right? So m, we were dividing it by m. And so let me go back a bit. Where was this equation? Okay, don't wait, I'll just show you. Yeah, right? So with respect to any theta, right, if we differentiate this equation, so let me just okay. So this is the equation, right? So here what let's say we are saying mean square error x, okay, and h naught, okay, is equal to, we are saying 1 by m. So here it's basically, we are saying for all of the thetas. I think I could do a better job here. So when we differentiate this with any of the theta, okay, when we say d of MSE with respect to say theta 1, okay, so what will happen is, when we differentiate, the 2 will come down, right? And it'll basically, this will convert into theta t x1 minus and so on. So with respect to theta 1, this is a constant, and this is also a constant, and this value is not a constant, correct? So out of this, because this is nothing but theta 1 and theta 2 and so on, right? So it'll look like 2 will come down, and it'll be theta t dot x minus y, and here multiplied by x. Why? Because this is essentially if you take a look at this equation, right, it'll be theta naught plus theta naught plus, I'm really bad at handwriting. Okay, let me try it again. So this is essentially theta naught plus theta 1 plus theta 2, and this is x1. Okay, this is x2 and so on. Okay, so this basically, this theta t is essentially this. Okay, so when we differentiate this with respect to theta naught, is going to be 1, and here, or we can just put x naught here. Okay, put x naught here. Okay, so what's going to happen is, for each of theta I or theta j, we can say, this is when we differentiate with respect to theta 1, it'll be 1 here. Okay, so 2 of this, it remains common, and when we differentiate this, everything else will become 0, and only x1 will be left if we are differentiating with theta 1. Okay, so that's how the derivation look like. Okay, all right. So this is the equation that basically comes after differentiating against every j. Okay, and for all of the j's together, the equation that comes out looks like this. Okay, it looks like this. Now, this formula involves calculation over the full training set X at every step. This is why it's called batch gradient descent. At every point, what we're going to do is we're going to compute this errors in every dimensions, in every theta, theta 1, theta 2, theta naught, and so on. So it's going to compute the errors in every dimension, and how it's going to compute? By using the linear regression, assuming that it's a linear regression, and using this differential way. Okay, so since batch gradient descent uses the entire training set every point, it is terribly slow at large training set, but gradient descent scales well with number of features. It is faster to train linear regression model when there are thousands of features using gradient descent than the normal equation. Okay, so the normal equation was great if the features were small. Okay, so while the gradient descent is great when features are huge. Okay. Gradient descent is good when the number of training sets are small. Okay, so because it's going to compute all of the MSEs. Okay, it's going to compute all of the errors with respect to not this. Yeah, so at every point of time, if you look at it, the this has to be summed up. This has to be summed up for every data point. Okay, for every data point. So this is something which we need to compute. Okay, mean square error, whatever we were provided with, was basically with respect to m, summation of all the errors with respect to every data point. And when we differentiated that, this still remains. So basically, this computation involves going through all the records in the training set, and therefore it is slow if the training sets are really huge. Okay, so gradient descent scales well with number of features, but not well with the large training sets. But normal equation is opposite. Okay, no matter how large is the training set, then normal equation works fine. But if the features are huge, then normal equation does not perform well. Okay, gradient descent. Once we have gradient descent vector, which points uphill, we basically go down in the other direction. So the next step computation. So we had some initial theta that we had assumed. Then we calculated the error. Okay, okay. We calculated the error. The next step of each theta, is going to be the previous value of that theta, previous value of that parameter or that dimension of parameters minus eta, which is this is called eta. It's the learning rate. Is the learning rate multiplied by the error. Okay, multiplied by rate of change of the error in that direction. So if the rate of change of the error is really high, okay, why minus? Because if the slope is positive, we are going uphill. If the slope is negative, we are going downhill. If we are uphill, we have to go in the other direction. That's why we have a negative, right? The next theta should be, we should increase theta if the next step of theta will be bigger, as in, so let me explain again. So if we are this is going to be negative, that's why we are having this. Okay, so next theta equals to theta minus the learning rate multiplied by rate of change of error with or you can say slope with respect to the theta. Okay, slope with respect to that theta. So this is the next step, and this we are going to compute for all of them together. So in a single step, we're going to compute all of the thetas from the previous value of theta by subtracting their corresponding uh, rate of corresponding slopes multiplied with the learning rate. Learning rate is same for all of the thetas. Okay. So here is a very simple implementation. Okay, here is a very simple implementation. We're going to use this formula to compute the rate with respect to each theta. So it's 2 by m xt dot x dot theta minus t. Okay, here is a very simple implementation. I think this will make it very, very simple to all of you. Okay, so we had xb as the features, y as our expected output, and y is the target as per our data. So We assume the learning rate to be 0.1, number of iterations to be 1000. Okay, and total number of data points are these many. Okay, now we are already given this data. All right, so here what we're doing is we are initially generating these thetas. Okay, here right now I think we have just taken two parameters here. Okay, I think it's just two variable equation. And then what we're doing is we are saying go iterate over these many iterations. And what we do is we compute the gradients. We compute the gradients for each of the value. So we are saying 2 by m into xb dot t, that is the dot t, the transpose of the matrix dot, and then we are saying do a dot product of this matrix with this. Okay, it's exactly the formula that we just talked about. Okay, and so we are going to compute all of the gradients in a single shot. This is going to be a list of gradients. Okay, and then we are saying new thetas are equal to the older thetas minus eta, which is learning rate, multiplied by gradients. Okay, let me show you. All right, I'm just going to comment this most likely. I was supposed to do only run above. Yeah, this is where we are. So here, so this is basically we are doing the random initialization of the weights. Okay, and I'm just wondering. Okay, yeah, this is better actually. Okay, so we here we have xb as this, as in capital X underscore b is this. Okay, we have so many values of x and so many values of y. Okay, so basically we have around 100 records, but there is only one variable in x. The total variables in x is 1. So that we have just seen, because it has only 2 columns. The first column is, okay, so you can see, so it has only one feature. So XB only has one feature, and so we are going at every point. We are computing the gradients. Okay, computing the gradients, as in the at every point we are computing the slope with respect to each of the coefficient, each of the model parameters. We are computing the slopes, and with respect to each of the slopes, we are computing the new values of theta. Okay, so theta is nothing but two variables, and both the variables we are computing in a single shot. And this is where the linear algebra comes really handy. All the vector computations come very handy because we don't have to do it for all the variables separately. Instead, we are able to do all of that in a single shot. Okay, does it make sense to you? So this is very similar to the previous example that we had done earlier using this was using the normal equation. Okay, and okay, let me go up. This was using the normal equation, correct? It was 4.2 and 2.7, correct? And here we are able to get how much? We're able to get 4.2 and 2.7. It's very much similar to the original values. Is the algorithm clear to all of you? So this is basically the batch gradient descent algorithm. Balaji, Binta, Gigi, Gopi. Yes, go ahead. Kamal, Nirav, Noor, Pavan, Pratik, Ross, and Shahrukh. All good? This is still finding the local minima. But the thing is that since we are starting with random initialization weights, right? So there are two parts. One is initial weights and other is eta. Okay. So if theta, the initial values, if we are choosing randomly every time, the result could be different every time. Okay. And sometimes we would get on the local minimas. All right. So it will be basically finding the local minimas. Okay, so I'm coming to that part very soon. Noor. All right, so this was our quick implementation. Okay, this was our quick implementation of the gradient descent. All right, so the first step is learning rate. Second is number of iterations that we want to stop. So here we are not saying stop at a certain point or at a certain rate, but stop when 1,000 iterations are finished. So here there are many constants that we are defining. One is learning rate. Second is the iterations. Third is the initial weights here, and so on. So you can think of all of these as hyperparameters for now. Okay, and we can talk about these in more details. All right, so at every point of time, we are finding the gradient of the cost function with respect to each of the thetas. So these gradients are 2 in numbers with respect to each of the thetas, and that's how it is. So output is this kind of an array. Okay, now the learning rate that we just did, if we basically choose huge learning rate or very small learning rate, there is a huge difference. If the learning rate is very small, say for example, here, let's say this is our target and this is our input parameters. So we want to find out this line that goes through this, right? So first it is going to try this, then this, then this, then this. This is how it is going to go. If the learning rate is slow, it's going to go slow. Okay, but if the learning rate is little bigger, say 0.1, it's going to go a little faster. Okay, going to go a little faster. But If the learning rate is huge, say zero point 0.5, what will happen is it will keep on jumping. First it tried this, then went there, then tried here something, then tried something. It would never try the line that is closer to this. Okay, it is similar to what we were talking about. The cost function, it will keep on jumping on the both the sides of the minimum cost. Okay, because learning rate is so huge that the thetas are generally, first they were very small, then they became too big, and so on. Okay, therefore we need to choose learning rate very wisely. Learning rates are okay. So if learning rate are very small, algorithm takes long time to reach optimum. Okay, because if learning rate is too small, here, if learning rate is too small, where is the learning rate? Here, if learning rate is too small, thetas will change very slowly. If learning rate is too huge, thetas will change very fast. If they change very fast, in both the cases, they will keep on jumping beyond the minimum cost. Okay. So this is how the learning rates impact. All right. So now question that we keep on talking about is how to find the good learning rate. Okay. So remember the grid search from end-to-end project. Okay. We can use grid search to find good learning rate. Okay, but we limit the number of iterations so that grid search can eliminate models that are taking too long to converge. Okay, question from Kamal. Would it not be better to define stopping criteria to slope of the cost function becomes, yeah, that is one of the things that we'll discuss. Nirav's question is, what is the value of y? Okay, so y is basically here. This is the generated data, right? For X and Y that we did earlier, where we created some noisy data. It is that data. Okay. So when it is optimizing the theta values, it's trying all possible slopes and all possible intercepts. Correct? So first it tries this, then this, then this, and so on. The only difference is the way it is going to try these lines are in a way such that both both the theta values, both slope as well as y-intercept is going to be optimized very quickly. In case of linear equation of two variables, right, the model parameters of thetas are nothing but slope and the y-intercept. All right, did I answer your question, Nirav? Okay, now first of all, to find a good learning rate, we use the grid search from end-to-end project, right? The one that where we discuss the grid search. Okay, but we limit the number of iterations so that grid search can eliminate models that take too long to converge. Okay, so we limit the number of iterations. Okay, if the iterations are just too many, then it will consume, each of the models would take a long time, and therefore we can limit the iterations. Okay, then how to set number of iterations? So next question is how to set number of iterations. Find the number of iterations. If the number of iterations are too low, then we may not get optimal solution when the algorithm stops. If the number of iterations are too high, then our time may be wasted and algorithm may never converge. Okay, so if the number of iterations that we are talking about here are too low, the algorithm it'll basically take, when the algorithm stops, we may not get good output. If the number of iterations are too high, a lot of time could be wasted and it may never converge, like if the learning rate is too high. So essentially, So we set a very large number of iterations and interrupt the algorithm when the gradient descent becomes very tiny. Okay, so we can interrupt the algorithm when the gradient descent becomes very tiny. So when okay, so if when the slope at any point of time, the slope of any point of time becomes smaller than some tolerance, then we should stop. Okay, we should not just keep going there. So we set a very large number of iterations and we stop at some tolerance as suggested by Kamal. And so for mean square error, okay, all right. So for mean square error, the batch gradient descent with a fixed learning rate has a convergence of this. Okay, basically, the more the number of iterations are there, okay, if the learning rate is fixed, the more the iterations, higher is sorry, the rate at which things are converging will keep on going smaller. Okay, so how should I explain this? So let me explain this. So okay, if the slope is smaller, it will require more iterations to converge. That's what it means. Okay, if the slope is smaller, it will require more number of iterations to reach or converge. Okay, and to reach to the local to the minimum. So if we right, the ball will roll faster. So here, this is the tolerance when if with respect to the individual slope. So yes, so if the tolerance is low towards the lower values, so when we decrease the tolerance or the smaller value to which we want to precise, okay, so the number of iterations will become 10 times more. In this kind of a graph, if we have say here, okay, here to go delta, right? To go say this much amount, it might require huge number of iterations. Okay, while going from here to here would be really quick. Okay, because here the rate of change is very small. So if we are saying here, if we are saying here that we start with a lot of number of iterations, say huge number of iterations, and then when the gradient vector, the slopes become lesser than a particular tolerance, then we would stop. Okay, we would stop or we will interrupt the algorithm. Correct. So if this tolerance we decrease a bit, suddenly the number of iterations will grow higher. Okay, so if it decrease the tolerance by say 10 times, the number of iterations will become 10 times. Okay, so basically the idea is that we start with a good so to find a good learning curve, we could use this technique. Okay, so at a we basically stop the moment we reach some kind of a tolerance. Remember that we can choose good enough tolerance. Okay, we should not we so if we choose the tolerance really small, the number of iterations are going to be really high. Okay, all right, so keep this in mind, uh, Okay. All right. So that's how we can generally figure out a good learning curve, right? A question from Noor, can't we make learning rate to adapt? Learning rate is something that we figure out based on the curve, okay? A question from Gopi is, so this is the stopping criteria. We basically choose a stopping criteria here, okay? If within certain values, make a big jump, otherwise small jump. Yeah, okay. So here, please keep in mind that we are stopping either when the iterations are exhausting or when the tolerance is met. So one of the fears that we have is we may stop before we have reached an optimal solution. Okay, so before even we reach the precision. So the answer to that is that the bigger values will be converging really fast as compared to the smaller value. Therefore, even if we are stopping before we are reaching the tolerance level, we would be good. We would be in a good shape. Okay, because it is the lower side of the tolerance which is consuming more number of iterations than the upper side. Okay, so yeah, answer from Kamal that we are doing that. The jump is learning rate into the slope. That's right. So the output is a function of multiplication of the two, slope and the learning rate. And but we are not adapting to learning rate is not adapting. Learning rate is a fixed value. Okay. Yeah, it is basically like a distance formula. Here we're basically summing up all the norm vectors, and that's it. So we are summing up all the gradients. We are summing up the squares of all the gradients and computing if that overall uh, slope is 0 or not. Okay, this is basically similar to saying differential of a cost function should be equal to 0. Okay, at the point of the lowest of the minimum point, at the point of minima or lowest cost point, the slope is supposed to be 0. Okay, and here we are introducing that tolerance. So we are saying that the overall slope should be within tolerance because have we can never have it as 0. Okay, great. So this is where, okay, so a question from Vinta, what are x1, x2, x3, xn? They are basically, I'll just show you in this is basically this, okay, the gradients. So all we have to do is say gradients square, and then we sum it up. We compute the sum of this. Okay, if the sum is less than, say, some amount of value, then we break. This is what it is. Does it work? You can see that as if the precision is really high, okay, Okay, so all right, you got the idea now, Vinta. We basically, it's x is basically gradients, and there we are squaring it up and summing it up. Okay, so we can plot the learning curve like this. All right. Now let's start with the stochastic gradient descent. Okay, so yes. All right. Now, in case of the batch gradient descent, it was taking just too many iterations. So it is slow when the training set is large because it has to try all possibilities, as it uses the whole training set to compute gradient at every point of time. So that's where the stochastic, that's where the stochastic gradient descent comes into play. It just picks a random instance in training set at every step and computes the gradients based only on that single instance. So yeah, this sounds very strange to you, but at every point of time, instead of computing the overall slopes, overall costs based on the entire data set, so what it does is at every point, it goes and computes the slopes around around all the data points for each of the thetas. For each of the thetas, it computes the slopes for each of the data points. So m into n times. For all of n thetas, it computes the slopes with each of the m data points, and then finds those. It finds the overall RMSE value of that. So, so that is basically the right. Is basically the it basically consumes too much of CPU cycles. So to avoid that, we have stochastic gradient descent. It just picks up a random instance in the training set at every step and computes the gradient based on that single instance. This makes the algorithm much faster as very little data gets manipulated at every step. So for each of the thetas, it just picks one random instance and computes the slope or gradient at that point. Also, Hughes training sets can be trained. Okay, Hughes training sets can be trained, as in no matter what is the size of the training data, since it is picking only one record, it can do it really quickly. So it doesn't need to load the entire data in the memory. It just need to load one record at a time. Okay, SGD, stochastic gradient descent, is a great candidate for online learning. Okay, when your requirement of learning is online, as in it has to be really fast. In that case, what it does is, while computing the slope, instead of computing all possible slopes with respect to all possible input data, it just computes it with respect to one of the data points, randomly selected, and then based on that, it does that. Because of which, it keeps on going little erratic, because it just depending on one data point. Okay, therefore it takes either too much time to converge, or sometimes it may not at all converge, but it is extremely fast. So instead of gently decreasing until it reaches minimum, the cost function bounces up and down and decreasing only on average. Over time, it ends up very close to the minimum, but once it gets there, it continues to bounce around and never settle down. Okay, because when, let's say, you're computing some theta, and the new theta, you're putting in the only one of the one of the data points. Okay, so at any point you are just fitting only one data point and then trying to predict the next learning rate. Therefore, the chance of error is really high, and hence it keeps bouncing before reaching to some value. So it is fast, but it can go wrong more than BGD. That's correct. Once the algorithm stops, the final parameters are good, but not optimal, as the algorithm never settle down. So when the cost function is very irregular, SGD has a better chance of finding global minima. So this is something that SGD help. So when the when the when the when we use SGD, the stochastic gradient descent, it will first try this and then randomly pick something and check this value against a data point somewhere here. And so basically it'll keep on trying values. It'll keep on trying the values in various uh, subsets of the data, and therefore it finding the global minima, the probability of it finding the global minima is very high. Okay, so because the randomness may help the algorithm jump out of the local minima. Okay, a question from Noor. Why not divide the data into batches and do distributed computing with BGD? Okay, so distributed computing is not that straightforward, though it's a very good idea. And around that idea only, Mahat was designed, and a couple of more algorithms have been designed around exactly that idea. Okay, the only difference is that when we compute the when we compute the what do you say, okay, let me go back to the point. So so what is Noor's suggestion is that we could divide a huge data into the batches and then send it to individual machines and let there it be solved by batch gradient descent. Correct. But how do we reach to the overall conclusion? So deviation from what you're suggesting is a very good idea, and a deviation of that one is what they have implemented in distributed, say, MLlib and others. Okay. Yeah. So so the other thing is mostly the data is not that huge. Yeah. Mostly the data is not that huge. Data is generally um, in megabytes. And when we are transferring megabytes over the network, the advantage that you get is not that big. Okay, that's another thing to consider. Okay, but yes, in case data is bigger, we do move to the big data side. All right. All right. So So on one hand, we have batch gradient descent. On another, we have stochastic. Batch is slow, while stochastic is fast, but error prone. So we need a better solution. We need somewhere in between, and that's where the stochastic batch gradient descent comes into play. Okay. Okay, we'll talk about simulated annealing and other parts in the next session. All right. So That's correct, Kamal. So HDD picks a random instance in the training set at every step to find out the gradient. And yes, few bad data points in the dataset can make it really go here and there whenever those get selected. Is there a way to avoid it? So a correct way to avoid those data points that would be maybe we can just do an outlier detection. Okay. And the pre-processing of data as discussed in the session 1 of end-to-end project could also help that. All right. So thank you, everyone. I look forward to see you in the next session. Okay. I know that we are going slow in this one, but what we have done is we have learned many things and refreshed many things. Rest of things are growing faster and faster as we are learning more things. So as we go forward, things are going to be faster. A question from Bintao is regarding that. So we have scheduled the um, deep learning, keeping in mind that machine learning is going to take some time. Okay. So it is just after finishing the machine learning. Okay. So we are not taking a gap. We reviewed the course curriculum based on our learning rate and we changed it, changed the time. All right. So based on our learning rate, we realized that that machine learning course may end towards the 24th of February. So from there, we are starting the deep learning. Yes, deep learning will be at the same time, Gopi. Okay, question from Noor. Is there a graph or animation which can clearly denote more than two features with convergence? That's actually hard to put three things. A easier way would be to take two parameters at a time and then plot them. Okay, because more than three dimensions, it's actually impossible to imagine. All right, so thank you everyone. Look forward to see you next week. Bye bye. Have a good day. Okay. A question from Noor. I would love to learn big data, but do you think I should go for deep learning first or big data, or both can be handled together? I think both can be handled together. Okay. All right. So thank you, everyone. I look forward to see you next week. Bye bye. Uh, Gigi, I'm sending you the other meeting link. Okay. All right. I'll just send you the other meeting link. Bye bye.